Okay, we're going to look at lines in 3 dimensions, so in R3. Okay, so the parametric and vector equations for some line, L. Now this is going to look very similar to 2 dimensions, so we've done a lot of the hard work already in setting this up and getting an understanding of what parametric and vector equations look like in 2 dimensions. So now we're just going to transfer that information to 3 dimensions. Okay, so in 3 dimensions we're going to let M equal to ABC be a vector that is parallel to the line that we're talking about, the line L. Okay, and that means M is going to be the direction vector. Now in 2 dimensions we also call that the slope vector. Well, it's hard to call that the slope vector here because slope was defined as rise over run, or B over A, and in this one here it's not going to be so easily defined because we have 3 coordinates here, so we're not defining a slope here, so we're just calling it the direction vector in 3 dimensions. Okay, R naught is a vector from the origin to a fixed point that is on the line. Okay, and P naught is that fixed point on the line. They have the same coordinates, but remember this is a vector and this is just a point. Okay, and R, well, R naught is just OP naught. Okay, so R naught here is equivalent to a vector from the origin to P naught, so it's just a short form of writing OP naught is R naught. Okay, and R, well, I messed up here a little bit, so I have to fit in some words here with this little arrow here. So R is the any point on the line. So R is a vector from the origin to any point on the line, the x, y, and z, the variables. So it's a vector from the origin to any point on the line, and this is where we're going to get our vector equation now. So we're going to relate R in terms of R naught and M. Okay, so just as we've done before, this doesn't look like anything different than it did in 2 dimensions. Okay, so R equals R naught plus Tm, where T is a scalar, it's a real number, it's a parameter. Okay, so you're going from the origin to some point, so this is the translation vector basically, and then you're going parallel to the vector M. So first to R naught, to P naught through R naught, and then scalar multiples of M. Okay. So in terms of coordinates, we look at it like this: R is x, y, z, R naught, x, y naught, z naught, plus T times M, which is A, B, C. So these are the vector equations of the line. And from that, we can get the parametric equations. T is the parameter here, so T is written as the parameter. So x equals x naught plus T times A, y equals y naught plus T times B, and z equals z naught plus T times C. So we just have an extra coordinate now that we didn't have before in 2 dimensions. Okay, so the parametric equations then just look like this. Okay, so x equals x naught plus ta, y equals y naught plus tb, and z equals z naught plus tc, where t is any real number. Okay, so these are the parametric equations. Okay, vector equation, parametric equations. All right, so let's take a look at a quick example here that uses some actual numbers in this. So what I've done, I've called it example A. We're going to look at this as, okay, so a line that goes through some point P naught, which is 1, 2, 3, that is parallel to a vector M, which is negative 2, 3, 5. Well, the vector equation for this, so if we look at the form for the vector equation up here, R equals R naught plus Tm, well, R naught is going to be OP naught, so it's going to be 1, 2, 3, and then time plus T times M. Okay, so the direction vector goes here. And then the parametric equations, well, they look like this. X equals 1 minus 2t, so 1 minus 2t, 2 plus 3t, 2 plus 3t, and 3 plus 5t. And that's where we get the parametric equations, right there. Okay? So that's that examples, and so I've done a little drawing here of what something like this might look like, and I've just sort of made up some numbers here. So this is a different example just through drawing. So I've made up some numbers here. So this is there's a lot of lines on here right now, so I'm going to try and explain it just a little bit. So we've got the x-axis, the y-axis, the z-axis, and then I picked some point P0 here. I said, well, let's make this negative 3, 2, 1. So how do we find that? Well, we go negative 3 on the x-axis, 2 on the y, and 1 in the z. And that gets us that point P0. And then R0 is the vector from the origin to that point. So I've written it down here as R0. Okay? So I'm going to zoom in a little bit more here. You can see it a little bit better. So R0 is right here, this vector from the origin to that point. M, I decided, was going to be this vector 3, negative 1, 3. Okay? So 3 on the x, 3 on the z, and then negative 1 in the y gets me that point there, and the vectors from the origin to that point, and that gives me the direction vector. Okay, so I want a line that goes through P0 and parallel to M. So what I did was I started with R0, so R0 plus M. So here's vector M here. I just translated it up there. And when I use the triangle law, R0 plus M gives me this red vector here. So that's R0 plus M. R0 plus 2M gives me this red vector. R0 plus 3M gives me this red vector. Okay. I can go the other way. R0 minus M gives me this one here. And R0 minus 2M, okay, so this one here gives me that. So the 1M, 2M, 3M, negative 1M, negative 2M, those are all values that you put in for t. And you can see that these red vectors all come from the origin and they fan out, but they end, their limit is this line that's in 3 dimensions. And we talk about lines in 3 dimensions. They're a lot more interesting than the ones in 2 dimensions. For example, the ones in 2 dimensions, they all have at least one intercept. So when they're written without restrictions, they all have at least one intercept. So they're either vertical, horizontal, or diagonal. Okay, so you'd have a XYZ axis like this, or sorry, XY axis like this, and you could have a vertical line. It's going to have one intercept. You can have a horizontal line. It's going to have one intercept, so a y-intercept, x-intercept for a vertical line. Or any other line would have 2 intercepts. Okay, an x-intercept and a y-intercept. However, in 3 dimensions, if you can imagine this, just imagine the 3 axes on your floor and going up one of the corners of your wall, and you just hold a ruler randomly in any position in your hand, and imagine where it might go compared to the axes. It's most likely not going to hit one of the axes. So lines in 3 dimensions probably will not have an x or y or z intercept if it's just randomly chosen.